Hey everyone, and welcome back to another CTF Writeup video. So I'm doing things a little bit different today. I'm using a tablet, and I figure we'll do some whiteboarding. If it's useful, please let me know. If it's not useful, also please let me know. So this challenge was Pwn Pandora. It was a medium easy CTF challenge as part of Cyber Apocalypse 2023. In this challenge, we're going to be doing some buffer overflows. We're going to then ROP to do a libc leak, and then we're going to jump to system and call bin shell. So the outline for the rest of this is we're going to set up, we're going to play with the binary for a little bit, we'll jump into Ghidra, see how things are laid out, we'll whiteboard the solution, and then we'll jump into the solve script where I have everything implemented in Pwn tools, and then we'll run it on the remote system, get flag, and that'll be it. So with that, let's get started. So for the challenge, exit. They give us a couple of different files. Specifically, they gave us this binary called PB, and they also gave us an example flag.txt, and then the rest of the stuff. And they also gave us a glibc, which was very nice. So if we run it, let's first jump into an Ubuntu box. Let's call PB. It says, this is one of Pandora's mythical boxes. Will you open it or return it to the library for analysis? We can click open. It says, what have you done? We are doomed. So I guess we're not supposed to do that. We can return. We can give it some value, and it says, we will deliver the mythical box to the library for analysis. Thank you. So not too much going on. We could try doing a buffer overflow there. I mean, it's the only input, so it must be. But we can take a look in Ghidra instead. So let's do make Ghidra. All right, now that Ghidra is loaded, let's take a look at the functions. First we go to main. You can see it's going to do setup, which is probably just doing some buffering. Yep. Then we go back to main. This is probably clear string. Then it's going to call banner, and then it'll call box. So the main stuff is probably in box. It's going to do some writing, read a number. If we gave it option 1, what have you done? We are doomed. Otherwise, it's going to do a gets on a buffer. So this is our in buffer. I just typed L so we can rename it. So it's going to read in OX 100 bytes into in buffer. If we look at in buffer, it looks to be maybe 32 bytes. So we definitely have a buffer overflow, and that's it. So nice simple binary. I love these. If we take a look at what protections are enabled, we can do make Checksec. We have full rel-row, so we're not going to be overriding the global offset table, but we will be using the global offset table as part of the exploit. There's no canary, so we have an easy buffer overflow. NX is enabled, so we're not going to be writing shellcode. We're going to be ROPing. No pi is enabled, so we don't need a main section elf leak, but we still need a libc leak, which we'll talk about in a second. And otherwise, that's it. So we kind of have our goal. We have a buffer overflow here. Since there's non-executable stack, we have to ROP. And from here, we just have to get shells somehow. There's no like ret to win sort of thing, so the goal definitely is to get shells. So either we need to do a one gadget, or we need to call system. Since the global offset table was full rel-row, we're not going to be overwriting any entries in there. So it most likely means that we're just going to jump straight to a system call while ROPing. And yeah, so I was going to try whiteboarding the solution, and if it's useful, sweet. Just to kind of put everything into context for about what we're about to do. So if we remember, the stack is laid out like this. Process memory is laid out like this. At the very top, we have our main elf. And so this is the binary. And at the very bottom, we have our stack. Here we have libc and all of our other libraries that are loaded in. And then, you know, there's other stuff in here, like there's we'll call this the elf data. And this is our instructions. Technically, it's called the text segment. Cool. So when we first start out, we're going to be doing that buffer overflow. And so what's happening is RIP is somewhere in here. So we're executing instructions, but that variable is defined on the stack somewhere over here. So if we zoom in on the stack, we have that data buffer that we're reading into. We said it was like 32 bytes or something like that. We'll just call it inbuff. I think we said it was 32 bytes, so we'll say each one of these is 8. After that, we're going to have the RBP. So eventually when we leave this function, this is going to be popped off, and RBP and RSP are going to be updated. So we'll just say RBP. And afterwards, we have the juicy target, which is our IP. So normally, if you use this correctly, you're only going to put in 32 bytes of buffer, but we're evil, so we're going to do more than that. When the function exits, it's going to call that leave instruction, which is going to pop off RBP and set RSP and stuff. And then the very last thing, the thing we're most interested in, is it's going to pop off RIP and set that pop off this value off the stack and set it to RIP, our register, and so we continue where execution is going. Like I said, we're going to be doing a buffer overflow. Let's change colors. White. So we're going to be overriding this with a whole bunch of A's, AAA. We're going to assign some garbage value here, so just that we don't mangle anything too much. But then we start doing our ROPing. And so we're going to put a return address here that we like. So it'll be, ret1. And then we're going to put another return address here of something interesting, and then another return address here. And I think in total, we're going to be using 4 of them. So since non-executable stack is on, we're not able to inject our own shellcode, but we're able to jump to existing places or other existing code gadgets. And so what we're going to be looking for are existing code fragments in here. So this is a read and execute only segment. So we can't write our own interesting stuff, but we can reuse interesting components that already exist within the ELF segment. And so we're going to be looking for a couple of gadgets. The first one, actually, PwnTools is going to be looking for the gadgets for us, but we're drawing out what PwnTools is doing behind the scenes. So what's going to happen is this is going to return, and the first thing we're going to look for is a pop RDI instruction. So somewhere in here, like maybe here within the text segment, there's going to be some assembly that does pop RDI, and what's going to happen is and then it's going to call ret. So at the end of some function, somewhere, this code already exists. And so what's going to happen is it's going to pop the next value of the stack. So technically, we're going to have a value right here. And it's going to pop this value off and set it to RIP. And so it's going to do this instruction. It's going to jump here. It's going to pop off the value. And then when it calls return again, this is the next value on the stack. So it's going to execute our second return address. From here, we're going to pop off the value of a global offset table, which I'll talk about in a second. And then we're going to call puts on that. And so what's going to happen is we're going to pop off a value that points to libc so that it will then print it. And then from there, we're going to return back to the main segment. So we're just going to start the function again so that we can do this exploit twice. So like I said, the value, let me erase this stuff. So we're doing that ROP chain just to pop off a value and put it into RIP so that we can print it. And the specific value that we're popping off is something in the global offset table. So the global offset table, it's going to be somewhere in here. It's a readable, right? Actually, with full row, it might only be readable. I think it's only readable. So it's either readable, writable, or just readable depending on row protections. But it's just a mapping that tells you where the offset for a function is within a library you're importing. So within our main ELP binary, it needs to call the libc functions like puts and exit and stuff. But when the developer is writing and when we're compiling the binary, it doesn't know where that library function is going to exist. So it's not too complex of a mechanism. Basically, we just need a lookup table that tells us, this is where the address is, this is where the address is for the function once it's loaded into memory. Because of, the address space layout randomization, libc could be here, or, it could be shifted up a couple thousand bytes or shifted down a couple thousand bytes. Like we want it to be random. And so we just need a lookup table somewhere. And, that lookup table, the global offset table, just exists somewhere over here. And so when we need to call one of those functions, obviously this all happens behind the scenes. It's just going to look up like, hey, where's this function actually located? It's going to get the address here. And so then the PLT can eventually jump, if we're calling puts, it'll say, oh, the address is here, and it'll jump to puts, and it'll call puts correctly. All happens behind the scene, all incredibly fast. But it's useful for an attacker for a couple of different reasons. One, it's a good leak target. So we have a mapping, the global offset table here, that contains all these addresses, and they're at a known offset. So I think this binary, since pi was disabled, I think it's 40,000, I think. I could be wrong, but it starts with a 40000. I forget how many zeros. This address will be like, I forget, maybe like 43, something like that, 4310 or something in that range. And it's always at that known position. So if we want the address of, I think we're leaking the address of read, which is another libc function, it's going to be at a known offset. So we're going to pop the specific value, and this value in memory is going to have the libc address for that call for read. And that's useful. So as soon as we leak that, we have a value of libc, and the base between libc, so libc is going to start at 0x7ff something 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 something. The difference between where the read code is and the base of libc is always a constant. So libc is going to move up and down in memory, but it's always going to be, 0x537 bytes away from the base. Cool. So that's going to be our ROP payload. So pretty cool. Once we have the address for libc, so sorry, going back, we're going to then call puts on it. Again, there's another thing in here called the PLT. which is what we can actually use to actually call functions. So we're going to put that address into RDI, and then when we call puts, we can then print out that address. Puts will just print it out, and then we're going to jump back to the main, the top of the function, whatever that function was called, just, you know, the main, like, whatever, where do you want to put it in the library function. Cool. So once we've leaked the address of libc, the rest of it's pretty easy. We're going to ROP again, but since we know where libc is in memory and we have that, we control RIP, we can jump anywhere. We're going to use, again, a pop RDI gadget, but this time, instead, we're going to, somewhere in libc, the string bin shell actually exists. So I don't know, let's say it's like right here. If we can, and it's at a known offset from the base of libc. So we can calculate, you know, where's bin shell, maybe it's at, you know, OX7F, blah, 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 I don't know, 3170. Maybe it's at this. So it's just going to be this far away from the base of libc. We'll figure out what that value is, and then we'll just call system. And basically, we're going to pop bin shell into the address of bin shell into RDI. So we're going to use that same RDI gadget. And then we're just going to jump to system. System's going to look at RDI. It's going to see it has bin shell, and it's going to execute bin shell for us. And then we have shell. So yeah, that's our game plan. To see what that actually looks like all together, I have a solve script. Nice. It's really not too bad. So we're using pwn tools like always. I ignore warnings. I shouldn't, but I do. We load the elf in. We're going to start the main process. We're going to grab libc from the process because we'll need it eventually. Send line after. So we go back to the binary. So I'm going to, make Ubuntu. Then we're going to jump into PB. Yep. So the first thing we need to do is type 2 to start. So that's what I'm doing here. We type in 2. Like I said, step 1 is to leak the libc address. So we're going to the first thing I did was I calculated how many. Actually, let's do that real quick. We need to, when we do the buffer overflow, we need to know where we need to start our ROP chain. And so a very useful way to do this is you can use pwn cyclic, and basically this will just send a repeatable pattern to the process, and so we know exactly where the crash occurred. And so to do that, we just do pwn. Actually, we'll do p.sendLine, pwn.cyclic 100. And then we'll do p interactive, and we'll also do a pwn.gdb attach p. Cool. So we're attaching GDB to the process. We're going to send 100 bytes of random, not random, but I guess cyclic code. And so we can see exactly where the buffer flow occurs. And then we're going to call interactive on it. So jump into tmux, python 3, solve.py. A little bit slow. Cool. So we are in the debugger. This is the string we sent it. So this is generated by pwn cyclic. When I hit continue, we can see here is the value that would have been popped off the stack and set into RIP, but obviously GDB was like, or the process was like, hey, this is not a valid address at all, and so it stopped executing. But now we can copy this because we know this is going to be the start of where our buffer overflow occurs, and we put that here, and this will tell us, I guess the value is probably like 24 or 32 or something like that. We calculate this value. I also save the elf data address. This is just so we don't clobber things too bad. Let me make it one smaller, just so we don't get too many new lines. So also on that stock was the RBP, just to keep things nice and clean. It's nice if that's always points to a readable and writable section. And so you can just put in a value like this, or one of these somewhere in between. And so that way you know at least the stack should be down here. But we don't have a stack leak, so we don't know a stack address. So we're just going to say the stack is somewhere over here. You don't have to do it. It just keeps things cleaner, and sometimes things need to get pulled off the stack. And if you do this, it just makes your exploits slightly more reliable. Anyways, so we're going to start ROPing. So we're using pwn tools, ROP tools. Absolutely amazing. It does all the heavy lifting for us. So instead of us like looking for those gadgets, you could use a tool like Ropper. So before this, I would use Ropper. So we'll use Ropper. It's installed. Cool. We'll do Ropper files equal to pb, and we would look for the gadgets and do it ourselves. And so these are all the gadgets. Basically, we're just looking for anything that ends in return. So read the next value on the stack. And here's the pop RDI gadget. So this is all we really needed. But we'd grab this value and then we'd put stuff on the stack and we'd line it. But pwn tools is amazing. It does it for us. So we're basically saying, hey, pwn tools, call puts and give it the value of the global offset table entry for read. So this is at some address like, I don't know, we can even look at it. GDB. Let's go pb. We're going to go run. Cool. So if we look at the global offset table, so this is that mapping I was talking about. So we're looking at read. So at this address will always be the same, and it currently holds this value. So this is the value we're going to leak because it's in the global offset table. And you can see all of these are updated, and these are just all exact pointers. So like if we were to copy this, copy examine instruction at here, we can see this is the start of fgets. So pretty cool. So we're going to print out the value for this read, which is for this indication. Like obviously this value is going to shift up and down because of ASLR, address-based layout randomization, but currently it's at this address. And then we're going to jump to the top of that function. That function was called box. If we go back here, yeah, we can see this function was just called box. So again, ROP tool figures out the addresses and stuff for us. Because pi is enabled, it's nice and simple. It's always going to be like 400, something like that. Yeah, 400000. 1, 2, 3, 4, 5, 6. So 6 zeros. Cool. It also has this useful, Pwn tools also has this useful tool where you can do print rop.dump if you're curious what's actually happening. So we can actually take a look at that and see what type of ROP payload it's generating. I'm going to copy GDB. I'm going to put it here, and I'm going to get rid of this. Hopefully everything still works. Tmux, Python 3, solve. Cool. So here is where ROP tools is telling us what, or sorry, Pwn tools is telling us what ROP payload they generated. And it's the same sort of payload. We can see we have the pop RDI return gadget. It's going to set RDI equal to global offset table.read. So this is the entry for the global offset table.read value. Then it's going to call puts, and then it's going to call box. So super cool, does it for us. And here is actually those instructions. So this must be pop RDI 4050. Could be. And then got read. No, it couldn't be. Oh no, this is the RBP. So here's our base pointer that we were setting. And then this must be the pop RDI. Yeah, these values match. And then this must be the global offset table entry for read. Then this is puts, and then this is returning back to the box. So pretty cool. Then let's take this out. And we can, I guess, jump. Actually, we don't really need to jump anywhere. After that, it's going to print out the, let's get rid of this. It'll print out the value. Maybe we'll take a look at that. We'll just do a GDB attach here. Python 3 solve. We can see, so we said puts, I want you to call the value with the entry for the global offset table entry for read. And we can see it actually prints it out somewhere. We need a 7F. Here it is, I think. OA 7F, yeah, this is it right here. So this, we will deliver the mythical book for analysis, thank you. Then the function returns, then our ROP code executes, and then it's going to call puts on the address, which is here. Cool. And then it starts the rest of it starts the function again. So we're going to get more standard text. But we can see puts dutifully called, and it prints out our libc leak right here. So we take that out. The code's a little bit weird. There's probably a smarter way to do this, but basically I say Pwn tools, I jump to right before the address is leaked, and I say, hey, receive 6 bytes, and then left justify it with a bunch of null bytes, and then I do a pwn unpack 64. Maybe there's a cleaner way. If someone knows a cleaner way of doing it, please let me know. This is just what I've always done. And then we print it out, the leak. So this was our leak value, and then from there we can calculate to the base of libc. To do that, we do vm map. We see where libc currently is. So this is libc right here. So what we can do is the difference between this value and this value is always a known value. It's always like, 32,000 or something like that. Even though libc shifts up and down, the difference between that and that is always constant. So if you need to calculate the base, you just take we can actually update these values. We'd copy this. We're going to put it here. And we copy this one. Oops. And we place it here. And then so the difference between where read is and the base of libc is always constant. So this number is always, like I said, 32,000 or something. And so whenever we get a new leak, we can just subtract it from whatever a leak is, and we'll get the base of libc. So that's how you calculate that. And then on the next run, so we have our libc leak. The function returns to the top of that box function. We're going to say, yes, we want to play again. We're going to type in 2. We're going to generate another ROP payload. This time we're going to, within the libc elf, we can actually search ourselves. You can do search type string bin shell, and this will find it, and it did find it. So somewhere in libc, this string exists, and it's right there. And so we can print it out, examine string at this address, bin shell. And so what we're telling Pwn tools to do is find the address of this within libc. Again, it's always at a known offset from the base of libc. So once we find it, we know where it is. And then we say ROP tools, I want you to call exec CVE, exec VE, I'm not sure how it's supposed to be pronounced, with bin shell, and then we're setting null and null for, I think it's like environment and arguments. And then from there, we just send that payload off to the binary, and we should get shell. So we can try GDB, oops, what was that? Find GDB, did I cancel it out? Yep, so let's do Python 3 solve. Actually, let me clear. Python 3 solve. Looks like everything ran. We do an ls, and you can see we have shell. Super cool. So at this point, we can try running it against the remote machine, since it is still live. So let's copy these out. This is the address. And Python 3 solve. It's connecting. And there we go. We have flag. Cat flag.text. Return to Pandora. So super cool challenge. Again, I feel like I love these types of challenges. They cover all the fundamentals and basics. Like, you know, we're going through different sections. We're leaking the global offset table. We're jumping to libc. So cool. Thanks for sticking around. If you think the whiteboard was helpful, let me know. If it wasn't helpful, also please let me know. And I'll see you in the next write-up video. Cheers.